Today, we are going to explore the process of moving from the frequency domain back to the time domain. By the end of this lesson, you will be able to define the inverse Laplace transform, use a standard table of transforms to find inverse functions, and apply the linearity property to solve complex problems. If we have a function in the S domain, which we call capital F of S, the inverse Laplace transform allows us to find the original time domain function, small f of t. Think of it as the undo button for the Laplace transform. If the Laplace transform takes us from t to s, the inverse takes us from s back to t. In practice, we rarely use the formal integral definition to go backwards. Instead, we rely on our knowledge of forward transforms and a standardized table. Let's look at how this works. To find an inverse transform, we look for patterns in our function that match known Laplace transforms. On the left, you see the forward transforms we've learned before. On the right, we simply read the table in reverse. For example, if you see 1 over s minus 3, you identify that it matches the form of 1 over s minus a, where a equals 3. Therefore, the inverse is e to the power of 3t. Similarly, if you see s over s squared plus 4, you recognize the denominator as s squared plus 2 squared. This matches the cosine form, giving us cosine of 2t. Notice that the constants must match exactly. If the numerator doesn't have the constant you need, we'll have to manipulate the expression algebraically, which we will see in a moment. Just like the forward transform, the inverse Laplace transform is a linear operator. This is a crucial tool for solving more realistic problems. The linearity property states that the inverse transform of a sum is the sum of the inverse transforms. Additionally, you can pull constant factors, like alpha and beta, outside of the operator. Let's apply this to an example. Suppose we want to find the inverse of capital F of s equals 2 over s plus 3 over s minus 4. Using linearity, we can break this into two separate inverse transforms. Notice how we moved the constants 2 and 3 out front. Now, we just look at our basic table for the remaining parts. The inverse of 1 over s is 1, and the inverse of 1 over s minus 4 is e to the 4t. Our final result in the time domain is 2 plus 3 e to the 4t. By breaking the complex expression into smaller, familiar pieces, the process becomes much more manageable. Often, we need to provide a specific constant that isn't already there. Let's look at how to handle the sign transform when the numerator doesn't match. Consider the function 1 over s squared plus 9. Looking at our table, the denominator s squared plus 9 is s squared plus 3 squared. This looks like a sign transform, where k is equal to 3. However, our numerator is 1, not 3. To fix this, we multiply and divide by 3. This is a common trick in calculus and differential equations. We rewrite the expression as 1/3 times 3 over s squared plus 3 squared. Because of the linearity property, we can pull the constant 1/3 outside of the inverse transform. Now, the inside part matches the table perfectly. The inverse transform is sine of 3t, so our final answer is 1/3 sine of 3t. Always check your k value in the denominator first to see what constant you need to create in the numerator. Let's wrap up what we have learned today about moving back from the frequency domain. We started by defining the inverse Laplace transform as the operation that recovers our original time domain function from its transform. We saw that by using a standard table, we can quickly identify basic patterns. The most important skill to practice is the algebraic manipulation. Whether it is pulling out a constant using linearity or multiplying and dividing by a value to fix a numerator, your goal is always to make the given expression match a specific form in your table. In our next lesson, we will tackle more complex denominators using partial fraction decomposition. This will allow us to break down even the most complicated rational functions into the simple forms we use today. Before you go, take a moment to think about this practice problem. How would you split it up? What constants would you need to adjust? If you found sine of 5t plus 4 e to the 2t, you are right on track. Great job today!